Hey everybody, here are solutions to the practice final from Lee's 17B class. Um, this is in lieu of a practice final written specifically for Dedel, but only got so much time. So let's get going. Evaluate the following intervals. So this one clearly is going to be U substitution. We're going to let U equal cosine theta because that's the thing that's stuck in the denominator. The derivative is almost sine, it's negative sine. I would swap in the minus here and the plus here. You could say minus du is equal to positive sine theta, d theta. So I'm going to rewrite this integral as the integral of negative du divided by u. If you prefer, you can write that as negative the integral of 1 over u du, if that makes it a little bit easier to see that the integral is going to be the negative natural log of the absolute value of u plus c, plugging back in that u is cosine theta, negative natural log of the absolute value of cosine of theta. Let's see. Alternatively, it is also correct to say that this is the positive natural log of cosine theta raised to the negative 1 power, which is 1 over cosine, which is secant. Natural log of the absolute value of secant theta. Also, don't mind the eyeshadow. It's St. Patrick's Day, and my wife thought it'd be fun, so hopefully it looks nice. I can't really see it because you have to close my eyes to see it. All right, next one here. Again, looks like a u substitution. We're going to let u equal the natural log of t. Don't love these other variables, but fine. Our du is 1 over t dt. We exactly have that. So we're going to rewrite this integral as the integral. We're going to change those limits. Our 1 over t dt, that's our du. And our natural log of t squared is going to be u squared. I like to change the limits. Those are t values. So if t is equal to 1, then u is going to be the natural log of 1, which is 0. And if t is equal to 2, u is going to equal the natural log of 2, which is just the natural log of 2. So then we integrate, we get 1/3 u cubed evaluated from 0 to the natural log of 2. We plug in the natural log of 2, we get 1/3 times the natural log of 2 cubed minus 1/3 0 cubed. I don't really want to write that. What's your answer? All right, let's look at this next one. Integral of x e to the x. That certainly bears the hallmark of an integration by parts problem. So we're going to let u equal x, dv is the rest, du is 1 times dx. The antiderivative of e to the x is also e to the x. So our integral of x e to the x dx is equal to u times v minus the integral of v du. Just to make sure everyone's on the same page. That is my u multiplied by my v minus the integral of my v multiplied by my du. And then we continue. The whole point is to make this new integral easier to do. The integral of e to the x is just e to the x. So we're going to get x e to the x minus the integral of e to the x, which is e to the x, plus c. Indefinite integrals get a plus c. Definite integrals don't. And so moving on. The integral of x minus 16 over 2x plus 1 times x minus 5. I'm going to zoom in a little bit here. I feel like that might make it easier to see what I'm doing. Also, I will post these solutions so you can follow along as well. To me, this certainly looks like a partial fractions kind of problem, right? It's already the denominator already being factored. It's a really good clue that it's partial fractions. So we're going to say that x minus 16 over 2x plus 1 times x minus 5. Oops, that looks really gross, James. Is equal to a over 2x plus 1 plus b over x minus 5. And then multiplying both sides by our common denominator, we have that x minus 16 is equal to a times x minus 5 plus b times 2x plus 1. Picking the easier of the two easy values, we're going to set x equal to 5. We do that on the left-hand side, we get 5 minus 16 equal to, on the right-hand side, a times 0 plus b times 2 times 5 plus 1. Or in other words, negative 11 equals b times 11, which means b is equal to negative 1. Similarly, we pick a convenient value to make this part equal to 0. So here we pick x equal to 5 to make x minus 5 0. Here we're going to pick x equal to negative 1/2. which you can find by setting 2x plus 1 equal to 0. So we're going to have negative 1/2 minus 16 equal to a times negative 1/2 minus 5. A couple ways to deal with this. So one way you could think about doing this is by like adding this together and getting negative 11 or negative 11 over 2 or negative 5.5. Same deal here, you can get negative 33 over 2. But an easier first step might just be to multiply both sides by 2. You multiply everything by 2, negative 1/2 times 2 is negative 1. Negative 16 times 2 is negative 32. Negative 1/2 times 2 is negative 1, and negative 5 times 2 is negative 10. I could have picked negative 2, that might have been better. On the left-hand side, we have negative 33. On the right-hand side, we have a times negative 11. And negative 33 divided by negative 11 is going to be 3. There's certainly other ways to have dealt with this, but this seemed like a good way. So oftentimes when you've got an equation with fractions, one thing you can do to make it easier is multiply both sides by that common denominator and just get rid of those fractions. It's only true if you have an equation, not just an expression. Cool. So that means that we can rewrite our integral as equal to the integral of a, which is 3 over 2x plus 1, plus b, which was negative 1 over x minus 5. You could do a u sub here, but I don't think you need to. I'll say I would skip this up. I'm going to write, but this is my thought process. I'm going to think of this as 3 times the integral of 1 over 2x plus 1 minus, or plus negative 1, minus 1 times the integral of 1 over x minus 5. I wouldn't really write the minus, I'd write minus. But for this integral, you're just going to natural log of the absolute value of x minus 5. For this integral, you could do a u sub and let u equal 2x plus 1. Your du is 2 dx. You're going to divide it by 2. Or you say, I know I'm going to divide by 2 and get 3 times 1/2 times the natural log of the absolute value of 2x plus 1 minus the natural log of the absolute value of x minus 5. Let's see. I think that's enough work, personally. And again, I think you can really skip this step. I'm just imagining this as 3 times 1 over 2x plus 1, and this is 1 time or negative 1 times 1 over x minus 5. Okay. Integral from negative 1 to 1. Okay, before I even look at the rest of this, and I see there's a hint, but just negative 1 to 1 already is like, it might be an odd function. The integral might equal 0. So hint, tangent of x is an odd function. Right. So clearly, we're supposed to show the whole function here is odd, and then show the integral is equal to 0. Yeah, we're fine. Okay. Yeah. So we're going to say that f of x is equal to 2x to the 4th plus x squared times tangent of x. Now for f of x to be odd, f of negative x has to equal negative f of x. So we're going to look at f of negative x, which is 2 times negative x to the 4th plus negative x squared times tangent of negative x. That's going to equal to 2 times x to the 4th plus x squared, right? A negative x to an even power just stays as x to that power. The tangent of negative x is, well, since tangent's odd, tangent of negative x is equal to negative tangent of x. Which is equal to, if you bring the, so you have this times negative 1 times tangent. We can think of it as negative 1 times 2x to the 4th plus x squared times tangent of x. But that right there is our f of x. So it's equal to negative f of x. That means the whole function, the whole integrand is odd. So f of x equals 2x to the 4th plus x squared times tangent of x is odd. So the integral from negative 1 to 1 or negative 0.5 to 0.5 or whatever the limits of integration are, if they're the same as long as it's defined, that integral must equal 0. Determine if the following integral is convergent or divergent. Evaluate the value if the integral is convergent. Interesting. I don't love this question. I'm going to point out that this certainly looks to me like the integral from 2 to infinity of x minus 1 over the denominator factors as x minus 1 times x minus 1. So rewriting it, it's really the integral from 2 to infinity of 1 over x minus 1. Normally, I'd be a little worried about the value of 1, right? Because we're kind of canceling a factor where 1 is weird. But since this integral goes from 2 to infinity, we don't have to worry about 1. So now we're going to rewrite this as the limit as b goes to infinity of the integral from 2 to b of 1 over x minus 1. We're going to integrate. We're going to get the limit as b goes to infinity of the integral of 1 over x minus 1 is the natural log of the absolute value of x minus 1 from 2 to b. That's going to be the limit as b goes to infinity of the natural log of the absolute value of b minus 1 minus the natural log of the absolute value of 2 minus 1. You don't really need the absolute values for that because 2 minus 1 is positive already. Natural log of 1 is 0. But this part here, as b goes to infinity, the natural log also gets infinitely large. So this is going to be infinity, which means our integral diverges or is divergent. To me, this question feels a little bit weird. I feel like he was trying to make it kind of unnecessarily complicated by not just immediately factoring and writing it like this, but whatever. Yeah. Oh, more convergence, divergence. Okay, so similar deal here. The only place of concern is the infinity here, right? Not the x to the fifth would be, this would be undefined if the 0 was also in the interval, but it's not, so we're not worried. So we're going to rewrite this. Well, actually, so yeah, we're going to rewrite it as the limit as b goes to infinity of the integral from e to b of the natural log of x over x to the fifth dx. But then I'm going to do the integration by parts over on the side. So let me grab it. So on the side here, u equals natural log of x. My dv is x to the negative fifth dx, right? Because the things have to multiply to the integral. And natural log of x times x to the negative fifth dx is the same as natural log of x over x to the fifth dx. And then my du is 1 over x dx. My v is the integral of x to the negative fifth, which is x to the negative fourth divided by negative 4. So rewriting it, it's going to be u times v, natural log of x times x to the fourth over negative 4, x to the negative fourth over negative 4, sorry about that, minus the integral of v du, which is x to the negative fourth over negative 4 times 1 over x dx. The thing about these natural log ones with a power of x is if it's a natural log of x times x to some power, in this case, natural log of x times x to the negative fifth, when you get your new integral, it almost always ends up being the same power of x you've already anti-differentiated. If we simplify this, still have natural log of x times x to the negative fourth over negative 4, which I suppose I could simplify. If we bring up the negative 1/4, we get plus 1/4, and then we have the integral of x to the negative fourth divided by x to the first. Negative 4 minus 1 is negative 5. So you're integrating x to the negative fifth again. And you're going to get, I suppose if we simplify this, it's natural log of x divided by negative 4x to the fourth. And then here we're going to get 1/4. The integral of x to the negative fifth is x to the negative fourth divided by negative 4. And it might be worthwhile to write this as one fraction. So I'm going to rewrite this as, I'm going to multiply this by a 4 over 4 here. I'm going to write this as negative natural log of x times 4. Really smooth there. Minus 1 all divided by, so here you have a 16x to the fourth, here you have a 16, right, I factored out the minus or the x to the fourth. Interesting. Okay. Yeah, I think it's worth getting a common denominator here. It's going to be easier to deal with, I think. So now we're going to do this part here. Okay, cool. This is equal to the limit as b goes to infinity of the integral. This we just found out was negative 4 natural log of x minus 1 all over 16x to the fourth. Evaluated from e to b. Plug in limits of integration. You get the limit as b goes to infinity of -4 natural log of b minus 1 all over 16b to the fourth minus, now you plug in e and you get -4 natural log of e. Natural log of e is 1 minus 1 over 16e to the fourth. Now, this part here is an infinity over infinity. But the top is going to infinity much more slowly. In fact, if we use L'Hopital's rule on this part here, you would get the limit as b goes to infinity of the derivative of the top, which is -4 over b, over the derivative of the bottom, which is what? 4 times 16, 64b cubed. As b goes to infinity, you're getting something going to 0 on top and something going to infinity on the bottom. That's going to be a big old 0. So then you're going to be left with 0 minus -4 times 1. Let's see here. We have negative, let's just do it this way. -4 minus 1 over 16e to the fourth. So -5, so 5 over 16e to the fourth. That's our convergent improper integral. It converges to 5 over 16e to the fourth. Assuming I'm not making any silly mistakes. I just want to do a quick double check here. I feel like I could have made an error here, so I'm going to check my work here by taking the derivative of this expression over here. That's kind of gross, but we'll do it anyway because I feel like I should. So we take the derivative of -4 natural log of x minus 1 over 16x to the fourth. It's going to be equal to, so bottom. That seems worrisome. I feel like I could have made an error, which always is worrisome here. Derivative of the top is going to be -4 times 1 over x. Yeah, minus the top. -4 natural log of x minus 1 times the derivative of the bottom, which is 64x cubed. Over the bottom squared, which is 16 squared times x to the 8th. Oh, I think that's going to work out. 16 squared is 256, x to the 8th. So then simplifying here, we have a -64x cubed. Yeah, okay. So we get a -64x cubed minus a minus is plus 4 natural log of x plus 1 times the 64x cubed all over 256x to the 8th. No, that's going to work out fine. Yeah, okay. So then you distribute here, you get a -64x cubed plus 4 times 64 is 256, x cubed natural log of x, plus a 64x cubed. Those cancel, divided by 256, x to the 8th, and yes, you do get natural log of x over x to the 5th. Okay. Felt like it could have been a little dicey. Sorry about that. Didn't mean to waste your time there. All right, this one here is you have to split it up first. So it's going to be the integral from -infinity to 0 of x e to the -x squared dx plus the integral from 0 to infinity of x e to the -x squared dx. Sure. This one's a pretty quick use of. I'll point out that the integral of x e to the -x squared is probably going to equal something like e to the -x squared. Take the derivative of this. Sorry, you can't see that. Apologies. The derivative of this is going to be e to the -x squared times -2x. We're off by a factor of -2, so we throw in a -1/2. That is the correct antiderivative. I don't need the plus c here. Which looks like it's going to converge when x is going to infinity or -infinity. So dealing with each of these, this one first, this is equal to the limit as a approaches -infinity of the integral from a to 0 of x e to the -x squared dx, which is equal to the limit as a goes to -infinity, the integral of x e to the -x squared. Again, it's a quick u substitution. You would let u equal -x squared. I kind of skipped that step. Didn't kind of, I did skip that step. Because I could see that the derivative of this was that really easily. So here's my integral, -1/2 e to the -x squared, evaluated from a to 0, plugging your limits of integration, you get the limit as a goes to -infinity of -1/2 e to the -0 squared, okay, e to the 0, minus -1/2 e to the a sorry, negative a squared. Now, the squaring is happening before the negativing. For me, I probably do this. I probably write this as negative 1/2, negative 1/2, interesting. Minus minus is plus, and then that, oh, sorry, I forgot the limit, which is super important. Limit a goes to negative infinity. I might rewrite this if it was hard for me to see as 1/2e to the positive a squared. Then I can say that a is going to negative infinity, a squared is positive infinity, e to the infinity is super big, 1 over something big is super small. So we get negative 1/2. Or you could have said e to the negative a squared. The a is negative infinity squared is positive infinity, but then the negative makes it negative infinity, e to the negative infinity gets closer and closer to 0. The same thing's going to happen for this other half. So for this other half here, we're going to say that's the limit as b approaches infinity of the interval from 0 to b of x e to the negative x squared dx. We're going to end up getting the limit as b goes to infinity of negative 1/2 e to the negative x squared from 0 to b. We plug in into integration, we get the limit as b goes to infinity of negative 1/2 e to the negative b squared minus negative 1/2 e to the negative 0 squared. In this case, this part again does the same thing. B is going to infinity, infinity squared is infinity, and then the negative in front of that makes it negative infinity. So this part's going to go to 0, just like that part went to 0. And then we're left with a minus 1/2, so that's plus 1/2. So overall, the whole thing converges, and it converges to negative 1/2 plus 1/2, which is 0, which is not surprising because x e to the negative x squared is an odd function. So if it was convergent, it would have to converge to 0 because the limits are the same, right? Because it's negative a to infinity. If it was 0 to infinity, it would have converged to positive 1/2. Ooh, some word questions here. All right. Let f of t be the number of bacteria at time t. The bacteria population starts with 100 bacteria and grows at a rate of df dt equals t e to the negative t. Bacteria per hour. How many bacteria will there be after pi over 2 hours? So we have to find the function first and then plug in the value pi over 2. Okay. So we have to solve this differential equation, which isn't too bad. Yeah, that's right. Yep. So we're just going to integrate this and say that, cool, f of t is going to equal the integral of t e to the negative t dt. We almost did that integral before. It's integration by parts. U is t, dv is e to the negative t dt. du is 1 dt, v is negative e to the negative t. So that's going to be equal to negative e to the negative t times t, so negative t e to the negative t minus the integral of v dt, which is the integral of negative e to the negative t dt. Sorry, it's kind of a little scrunched in there, apologies. That's a plus, so that's going to equal negative t e to the negative t minus is plus, but then it's the integral of e to the negative t, so it's minus e to the negative t plus c. Then we're going to use our initial condition where time is equal to 0 and f is equal to 100 to solve for c. So f of 0, which is equal to 100, is equal to 0 e to the 0 plus negative e to the 0 plus c. So it looks like c is equal to, well, let's see, 100 equals negative 1 plus c. So it looks like c is equal to 101. So f of t is equal to negative t e to the negative t minus e to the negative t plus 101. And then I don't know why pi over 2 seemed like a good choice here, but f of pi over 2 is going to equal negative pi over 2 e to the negative pi over 2 minus e to the negative pi over 2 plus 101. The answer is definitely not an integer. Okay. Let's Sketch the region between the curves y equals sine of x, y equals cosine of x, and between x equals 0 and x equals 5 pi over 4. Find the area of this region. And they even give you a hint. They tell you where these both intersect, which is kind of nice. Nicer than I would be. So let's see. Sine of x, so 1. And then, sure, let's say, sure, I don't know. Let's just start with graphing sine. So sine, let's say we're going to go to, say that's pi. Here's your pi over 2. Here would be your 3 pi over 2. The sine starts at 0, then goes up to 1 and pi over 2, back down to 0 there, and down to -1 there. Cosine starts at 1, goes down to 0, then down to -1, then back to 0. So if we're between 0 and 5 pi over 4, and 5 pi over 4 is like right about there, there's their intersection of 5 pi over 4, there's an intersection of pi over 4. So if we're going from 0 to 5 pi over 4, this area here, we're going to get by doing the cosine function minus the sine function, right? This blue one is cosine, the black one is sine. So our area is going to equal the integral from 0 to pi over 4, right? They told us that's where it intersected. Of the top function minus the bottom function, so cosine x minus sine x, plus all this other area here, which is going to be the integral from pi over 4 to 5 pi over 4 of the top function minus the bottom function, which is going to switch. It's going to be sine minus cosine. That's it. Then we find the area. So we do the integral. So it's going to be the integral of cosine, which is sine of x, minus the integral of sine, which is negative cosine. So it's going to be plus cosine of x, valued from 0 to pi over 4, plus similar deal here, the integral of sine of x, which is negative cosine of x, the integral of minus cosine, which is negative sine of x, from pi over 4, 5 pi over 4. Sine and cosine of pi over 4 is equal to root 2 over 2. 5 pi over 4 is in quadrant 3, equal to negative root 2 over 2 for both of them. So here's what we're going to get. We're going to get, I would really probably skip this next step, but I'll write it out here. I would instead of writing sine of pi over 4, I would just write root 2 over 2 plus cosine of pi over 4 minus sine of 0 plus cosine of 0 plus then this right here, negative cosine of 5 pi over 4 minus sine of 5 pi over 4 minus negative cosine of pi over 4 minus sine pi over 4. That may be good to write if you didn't know what the values were, but these are clearly values we're expected to know. So we would write this out as root 2 over 2 plus root 2 over 2 minus 0 plus 1 plus negative root 2 over 2 negative root 2 over 2 minus and minus is plus cosine pi over 4 is root 2 over 2 minus is plus sine pi over 4 is also root 2 over 2. So it looks like we have 1, 2, 3, 4, 5, 6. So we have 6 times root 2 over 2 minus 1, or 3 times root 2 minus 1. All right, move on. Might have to pause this and stop halfway through because I have to go to office hours in a half hour here. Solve the following initial value problem. So this looks like we should probably separate it. So I have the dy dx equals x over x squared plus 1 times e to the y. Oh, sure, equals 0. Yeah. Separate. So e to the y dy on the left equals x over x squared plus 1 on the right times dx. Integrate both sides. Left-hand side is e to the y. Right-hand side is the natural log of I'm not going to use an absolute value here, and I'll explain why in a second. That's close. What's the derivative of natural log of x squared plus 1? It's 1 over x squared plus 1 times 2x. We're off by a factor of a half. In fact, if you like, you can throw in a 2 here and a 1/2 here. So that now, oh yeah, the 1/2 sticks around, and the derivative of the natural log of x squared plus 1 is exactly 2x over x squared plus 1. You don't really need to write the 2 and the 1/2 there, but you can if you want. And then a plus c. The reason I don't need the absolute value here especially, although I probably would have omitted it anyway, is x squared plus 1 is already always positive. So the absolute value doesn't need to be there. We have an initial condition of y of 0 equals 0. This is probably the moment to find it. You could certainly take the natural log of both sides first and say that y is equal to the natural log of 1/2 natural log of x squared plus 1 plus c. But if you're going to try and find c, you're going to have to undo that natural log anyway. So this right here, this is your moment to actually find your constant. So if I plug in 0 for y and 0 for x, I'm going to get e to the 0 equal to 1/2 times the natural log of 0 plus 1 plus c. Natural log of 1 is 0, so c is equal to e to the 0, which is 1. So really, I could have skipped writing this and said, cool, my function y, or y of x, is equal to the natural log of 1/2 times the natural log of x squared plus 1 plus 1. Kind of funky. Ugh, all right, so clearly he's giving us the first order linear solution here. He's using m of t instead of mu of t. I feel like that's weird, but why, whatever. This is not written in the standard form, though. We have to rewrite it. So again, the standard form is dy dt plus your function of x or y or t or whatever. In this case, the function of t times y equals your other function of t. So rewriting this, first dividing everything by t, we have that dy dt plus 2 over t times y minus t equals 0. And then bringing this here to the other side, we get dy dt plus 2 over t times y. 2 over t is our p of t equals t. So here's our p of t. Here's our q of t. Or I guess what he would call g of t. Terrible notation. So then our mu of t, or in his case, m of t, is e to the integral of 2 over t dt. We get e to the 2 times natural log of t, which is e to the natural log of t squared, which is just t squared. Since we don't have a lot of room, we are going to jump straight to the conclusion. I'm going to say that our answer, y, or y of t, is equal to, we're dividing by the integrating factor. I like to write it in front as 1 over your integrating factor, t squared, times the integral of your integrating factor times your q of t, which is going to be t squared times t. Which I would have just simplified as t cubed. So that's a t cubed. The integral of t cubed is t to the 4th over 4. So we're going to get 1 over t squared times t to the 4th over 4 plus c. It is vital that this 1 over t squared, interesting. I feel like the person writing this problem did not think it out very carefully. Yeah, they really didn't. So the 1 over t squared has to distribute to both terms here. Yeah, what are you thinking, dude? The problem so the issue here is this initial condition, right? You can't plug in 0 for t and get division by t squared unless I made a terrible error, which I don't believe I did. Let me double check here. Nope, I divided everything appropriately. Maybe he forgot there was a 2 there. I don't know. But I got 2. Yep, that looks right on. And then I integrated 2 over t. I got 2 natural log of t. Right? No, I definitely. So yeah, this problem, unfortunately, I don't think has a solution for the initial condition that was given. Sorry about that. I would distribute the 1 over t squared though and get t squared over 4 plus c over t squared. And then if you were given an appropriate initial condition, you could solve for C. That is wrong. Well, we'll check his solutions later and see. All right. Construct the phase plot, final equilibria, and determine if it's stable or not. So we have intercepts at 1, 2, and 3. Pick a number larger than 3, like 4. You can see it's positive, positive, positive. It's going to be positive over here, and it's going to cross every time. So it's going to be cross, cross, cross. Also, y of 0 would be -1 times -2 times -3, which is -6. So it looks something like this. Y prime, y. We can see that we're increasing right of 3. We are decreasing between 2 and 3. So our derivative is negative. We're increasing between 1 and 2, and we're decreasing left of 1. So it looks like 2 is the only stable point. So y hat equal to 2 is a stable equilibrium. Y hat equal to 1 and 3 are unstable equilibria. I think the picture is the justification personally. Yeah, I don't know what words I would use. All right. Let R be the region in quadrant 1 bounded by y equals 4x squared and y equals 4 and x equals 0. Draw it. Quadrant 1, y equals 4, y equals 4x squared. When x is 1, you're going to get y equal to 4. So it's going to look something like this. And x equals 0, which is right here. So we're looking at this region here. What is the volume of the solid generated by rotating r about the y-axis? We're going on the y-axis. Means we'd have to use strips that are perpendicular to our axis. So we have to use horizontal strips. This is definitely going to be the disk method, not the washer method, because our region is flush with the axis of rotation, or no matter where I draw my strip, it's always going to be touching the axis of rotation. So the volume of our disk is going to be pi times the radius squared times dy, because our thickness is a small change of y. If I actually draw this disk around here, not that you need to do this, but I'm just trying to help you see what's happening here, right? That's our disk there. The volume is the height, which is dy, times the area of the circle, which is pi r squared. That radius depends on where I draw the strip. So that radius is this right function here. But it's not y equals 4x squared. We have to solve for x in terms of y. So this y equals 4x squared. If we solve for x, it's even written in this way, I think, to make you think to solve for x. And we're going to get x squared equal to y divided by 4. X equals plus or minus the square root of y over 4. But it's certainly going to be the positive root because x is the positive value. We're in quadrant 1. So the volume of our disk is going to be pi times the square root of y over 4 squared dy. And then the total volume is going to be the integral from as low as y equals 0 to as high as y equals 4 of pi times the square root of y over 4 squared. My y's and my 4's look a little too similar there. That's a y on top of one on the bottom. The nice thing here is the square root and the square root undo each other. So we're really just integrating from 0 to 4 pi times y over 4 dy. The pi over 4 hangs out. The integral of y is y squared over 2 from 0 to 4. Plugging in 4, we get pi over 4 times 16 over 2. Plugging in 0, we get 0. That's going to be 16 divided by 8, so 2. Ooh, cracking my neck. All right, well, this next part's going to be tough to get done in time. Sorry, not this part, the next graph. So the x-axis, same sort of idea. So now it's going to be the washer method. So the strip is going to be like this. So that's our inner radius. That's our outer radius. The volume of our washer is going to be pi times the outer radius squared minus pi times the inner radius squared dx, because now the thickness is the small change in x. In this case, the pi factors out. The larger radius is just the top function y equals 4. The smaller radius is the bottom function, which was 4x squared. Because now it's in terms of x, not in terms of y. So the total volume is going to be the integral from x equals 0 to x equals 1 pi times 16 minus 4x squared squared is 16x to the 4th. Integrate, you get 16x minus 16x to the 5th over 5, from 0 to 1. You plug in 1, you get 16 minus 16 over 5. Plug in 0, and you get 0 minus 0. I would probably leave it like that if I was taking a test, but if I wanted to simplify it further, 16 is 80 over 5, and 80 minus 16 is 64. So you get pi times 64. All right. Consider the following recursion. Next year's population is equal to last year's population times the matrix A. Or I should say A times last year's population. Where A is equal to this matrix. Assume that A equals 0. Find the eigenvalues and eigenvectors. Okay. For the eigenvalues, we should do 0 work. The first eigenvalue is 2. The second eigenvalue is 1/2. If you have a 0 here, your eigenvalues are always just the diagonal entries. Okay. So then, sorry, something popped up. I need to close one moment. Okay, so then find the eigenvectors, usual deal. You're going to have 1/2, 1, 0, 2. So this is for lambda 1 times, we don't know, x, y equal to 2 times x, y. We're doing this one first. So the first equation is going to give us 1/2 x plus y equals 2x. Subtracting, you know what, let's make our life easy. Let's do the thing, so instead of doing 2y 1/2, even though it's pretty easy, let's multiply both sides by 2. So you have x plus 2y equals 4x, or 2y equals 3x. So my eigenvector is going to be x is 2, y is 3. Cool. The second eigenvalue, same deal. 1/2, 1, 0, 2 times xy equals 1/2 times xy. In this case, if you use the first equation, you get 1/2 x plus y equals 1/2 x. The x's cancel, and you get y equal to 0. And we've said this before, if one of the two things in the eigenvector is 0, the other component is any non-zero number you want, but we always pick 1. So our eigenvector is going to be, well, y is 0 and x is 1. Great. Moving on to part B. Maybe. Find the matrices P and D so that A equals PDP inverse. Cool. Matrix P is just the matrix of eigenvectors. You can pick it in either order you want. The only thing you have to worry about is making sure that the orders match up. So if we pick them in the order as written, this one first, this one second, our P is going to equal the vector 2, 3, 1, 0. The eigenvectors as columns. And our D is going to equal the diagonal matrix with the eigenvalues as in the same order. So we picked the first eigenvector to be 2, 3. The associated eigenvalue was lambda equal to 2. So that's what's going to go in the first column here. And then in the second column, the eigenvalue of 1/2. And then you find P inverse in the usual way. P inverse is going to be 1 over 0 minus 3. And then you switch the diagonals and you change the signs of the off diagonals. I wouldn't do any more work than that. I'll point out you could have made the other choice and say P is equal to 1, 0, 2, 3. And then D would be the diagonal matrix 1/2, 0, 0, 2. And then P inverse would be the matrix 1 over 3. Change the 1 and the 3. Change the signs of the 2 and the 0. Either one of these answers would be correct. Further assume that the initial vector your initial population sizes are 2, 1, and express the solution to the recursion in terms of the eigenvalues and eigenvectors. Okay, so all they're saying here is that we're trying to write that, right, he's even giving us the solution here. So NT, the population after T iterations, which would be equal to a to the T times Rn naught. We can write that as C1 times our V1. And I'm just going to make the choice to do it this first way. I actually don't think I need, I don't think I need this. C1 times my V1, which was 2, 3, times lambda 1, which was 2 raised to the Tth power, plus C2 times V2, which was 1, 0, times lambda 2, which was 1/2 Tth power. The thing though that we have to do here is we actually have to find what C1 and C2 are. When we do that is we express this initial vector as a linear combination of these two vectors. So we have to solve 2, 1 equal to C1 times 2, 3 plus C2 times 1, 0. It's always easy if there's a 0 there or anywhere, because then we know that C1 has to be 1/3. Because 1/3 times 3 is 1, and whatever C2 is you're going to add 0 there. And then find C2, well, C1, we have the 2 times 1/3 plus C2 is equal to 2. So C2 is 2 minus 2/3, which is 4/3. So I should have really just waited on writing this and said my solution is 1/3. I like to write the 2 to the t part first, personally. Times 2 to the t times the vector 2, 3 plus 4/3 times 1/2 to the t times the vector 1, 0. And the last part being this, what happens to the direction of NT in the long term? So this question is something we didn't really address in class, but what we're really asking here is kind of, as you let T go on and on and on, what's happening to your population size as well? As T goes on and on, this 1/2 to the T power gets smaller and smaller and smaller. So this part here, that part there becomes negligible, which I don't know how to, negligible, who knows? Unspellable. And then this part here is going to dominate, right? This 2 to the T is going to take over. So in the long term, the direction is going to point in the direction of the 2, 3 vector. So in the long term, lambda 1 equal to 2 dominates, and we point in a direction similar to the vector v1, which is 2, 3. And because at the end of the day, right, nt, if you add this together, is going to be some vector. So if you think about t being really, really big, these two terms are going to be, in proportion 2 to 3, and this is going to be insignificant by comparison, right? If t is like the 1,000th power, you're going to get 2 times a bajillion, 3 times a bajillion, and then here you're going to get practically nothing. So you're going to be pointing in the 2, 3 direction, plus like a tiny little sliver in the 1, 0 direction, which is going to be not important. All right, let's see. Can I finish? I think I can wrap this up and then head over to opposite sides. So if A is equal to 1, so same matrix, but now it's the matrix. So now it's the matrix. I might not be able to finish this right now because I'm going to take a minute. The matrix, where'd you go? Other page. Did I go to backwards? Sorry. If A is the matrix 1/2, 1, 1, 2. So 1/2, 1, 1, 2, instead of 1/2, 1, 0. So let me double check here. 1 second. Yeah. What happens to the direction of NT and what will happen to the magnitude of N in the long term? Okay. So it's really about finding the eigenvalues and eigenvectors. Okay, we can do this relatively quickly and be a little bit like that. So eigenvalues, determinant of 1/2 minus lambda, 1, 1, 2 minus lambda. But 1/2 is terrible. We have 1/2 minus lambda times 2 minus lambda minus 1 times 1, which is going to be lambda squared. And then we have a minus 2 lambda minus 1/2 lambda, so a minus 2.5 or 5/2 lambda. And then we have a plus 1 minus 1, which is, well, yeah, we're setting that equal to 0. So we end up getting the ones canceling, factor out the lambda, you have lambda times lambda minus 5/2, 0. So you're getting a lambda equal to 0, which is always sort of funky, and a lambda equal to 5/2. For lambda equal to 0, which I guess makes sense. Yeah. For lambda equal to 0, the eigenvector 1/2, 1, 1, 2 times xy equals 0 times xy is just 0, 0. Let's do the second row just because it's easier to deal with. 1x plus 2y equals 0. So you're getting 2y equals negative x. So x is going to equal 2. And y is going to equal negative 1. And then for the second eigenvalue, which is 5/2, determinant, or sorry, not determinant, 1/2, 1, 1, 2 times xy equals 5/2 times xy. We get 1/2 x plus y equals 5/2x multiplied by 2. X plus 2y equals 5x. 2y equals 4x. So y equals 2x. Our eigenvector is going to be x is 1, y is 2. These vectors are kind of orthogonal to, not kind of, they are orthogonal to each other. So then in the long term, interesting. Yeah. So our solution, yeah, let's go ahead and do the whole thing. So then we're gonna write this vector as a linear combination of these two vectors. So we're gonna say that let's find a ring here. So 2, 1 is equal to C1 times 2, negative 1 plus C2 times 1, 2. Well, sorry, you can't see that. Apologies. So ish solving this out. Don't love to do this work here. 1 second. So we have 2 equal to 2c2, 2c1 plus c2, and 1 equal to negative c1 plus 2c2. Multiplying the second equation by 2, we have 2 equals negative 2c1 plus 4c2. Adding this one and this one together, we get 4 equal to 0c1 plus 5c2. So c2 is equal to 4/5, and then c1, well, c1 is equal to 2c2 minus 1. So it's equal to 8/5 minus 1, which is 3/5. Using the work we have from the previous page, we can then say that our solution and t, or the tth iteration, right, because that's what they're asking about, is equal to c1, which is 8/5, times lambda 1, which is 0 to the tth power, times the eigenvector, which is 2, negative 1, plus c2, which is 4/5, times that eigenvalue to the tth power, which was 5/2, tth power, times the eigenvector associated, which was 1, 2. Clearly, this isn't going to contribute at all, right? In fact, it's a big old 0. And so in this case, the what's going to be the magnitude event in the long term? Apologies. Sorry, not apologies. I apologize. I read the question wrong. The direction and magnitude. So the direction is going to be the direction of this eigenvector, which I normally would have called v1 because it goes with the larger eigenvalue. So the direction is in the direction of the vector v2. And the magnitude of the vector n, well, if we let t get larger and larger and larger, sorry, you can't see that, apologies. This part's going to get bigger and bigger and bigger. So the magnitude of the vector n, I think, is just going to get larger and larger and larger. So the magnitude of n is going to go to infinity. Right? It keeps increasing because this solution here right? That part there is going to get larger and larger and larger if you let t go on and on and on. Yeah, I think that's all to say about that. Okay, I gotta go. It's 10:59. Yeah, if you have questions about this, please feel free to ask.